Hello and welcome back to this series of videos in which I take generative artwork sketches from the book Generative Design and apply them in the world of Max, MSP, and Jitter. This patch and this sketch is an interactive generative color grid. As you can see, the position of my mouse in this JIT world window is determining the resolution of the grid that is being generated. There are certain color rules applied to the columns and rows of this grid to generate a very specific palette of colors. Using this, you can generate some interesting motion as well as some interesting color palettes. Now, this is all done through jit.gen. I've created an algorithm in jit.gen that takes an empty jitter matrix and generates a grid and applies this color system based only on the mouse position. So this video is great for figuring out how to get the mouse position from a cursor on a JIT world window, as well as figuring out an algorithm that generates such a grid. This is a fantastic starting point for working with jit.gen, as well as starting to think in terms of generative interactive artwork. Let's see how this is done. All right, first of all, I'm going to create my visual output environment, meaning that I'm going to create a jit.world object with the argument being the name of this jitter world context. It can be anything. I'm going to call it color grid. I'm also going to give it the attribute floating set to 1 to make sure the resulting window is always on top of the patch, even as I'm editing the patch. I'm then going to create a toggle connected to jit.world so I can turn it on and off as it is necessary. And then I'm going to create a jit jitter matrix, jit.matrix. This jitter matrix is going to be the basis of our visual generation, right? It's going to have 3 planes, so each cell is going to have 3 bits of data associated with it, red, green, and blue values, because we are going to be working with the RGB color system. The data type is going to be float 32, and the dimensions are going to be 400 by 300. We can change this down the line if it's necessary. I'm then going to create a jit.gen. Inside this jit.gen, we are going to define our cool visual generation algorithm. That is going to be the meat of this video. But whatever the result is, the resulting jitter matrix, so the visual component, is going to go into jit.gl video plane. This object, jit.gl video plane, needs to have the name of the jitter world context as an argument, so color grid. And also, very important, it needs the attribute transform_reset set to 2. And you can immediately see this window is now completely black because it's entirely being covered by this video plane that we have created, no matter what the size of the window is. So the resulting jitter matrix is going to go here, and hopefully, after we have defined our complete algorithm, some cool visuals are going to appear here. Okay, so now let's see the model or starting point, the P5.js sketch. So this is again from the book Generative Design. This is the second sketch, and I think it is called color grids. For those of you who are comfortable with the JavaScript code, you can also look at the P5.js code and see how it works. You can see it's fairly simple, not too many lines of code, but it does result in some cool behavior. But once again, I'm going to be looking at the visual and interactive component itself and not the code. And I can immediately make some observations. So this is, of course, reactive to the position of my mouse. This is creating some kind of color grids, where each grid element, so all these columns and rows, have individual colors. And the resolution of this grid, so how many, let's say, grid elements there are in the sketch, is determined by the position of my cursor. So if it's very close to the top left, the X and Y coordinates of the mouse is taken as the width and the length of the grid element, and that is being used as the basis for the entire grid. I also see that as I go from left to right, I'm actually going through the circle of colors. I'm going through all possible hues, right? I'm starting with red and I'm going through all possible colors, and I end up at red as the circle is complete. But on the y-axis, so the vertical components to all these rows, change instead the saturation. Right, I'm going to do brightness in the max patch, but it is the saturation in this patch, in this P5.js sketch, I believe, that changes. So the changes in color are also 2-dimensional. Okay, so to make this work in Max MSP, or more specifically in Jitter, we need to figure out two things. First of all, getting mouse coordinates. And I'm going to say getting normalized mouse coordinates, and I'm going to explain what that exactly is in just a second. And two, this is the hard part, generating a grid from a static matrix. Right? What do I mean by static? I mean this matrix is already kind of a grid, it's 400 by 300, but I want to split this matrix in a grid of an arbitrary size dynamically, even though the matrix itself and the dimension of it is static. But enough talking about grids. Let's start with the easy part. Now I want to get the normalized mouse coordinates, and I want to do this without clicking on the screen, because you will notice that the third outlet of jit.world is going to report mouse information, the position, and if it is clicked or not, when I click on the window. It is not going to work if if I'm not clicking on the window and I'm just hovering my mouse above it, but that is what I want. And for that to work, I need to send a very specific message to jit.world. And that message should be, let's see if I remember this right, send window idle mouse 1. So if I send this message to jit.world, as you can see, the third outlet is going to send out data even as I'm not clicking on the jit.world window. It's going to say mouse idle and then the coordinates of the mouse and then a bunch of zeros, which are not important right now. So send window is targeting the window component of jit.world. Idle mouse is the setting or the attribute we want to change, and 1 is turning that attribute or functionality on. Since I always want this message to be sent to jit.world, I'm going to be using load bank. So I'm going to make sure that this message is sent to jit.world each time I load this patch. Okay, so then I use the word normalized here. I said getting normalized mouse coordinates, and this word normalized means between 0 and 1. No matter the size or the resolution of my window, no matter the possibilities of coordinates I might receive, I want the end result to be a value between 0 and 1 for both the x-axis and the y-axis. And here's how I'm going to do this. So first of all, I'm going to single the dimension or the coordinate of the mouse from the incoming message. So mouse idle and then those two values. And I'm going to do this by using two objects. First of all, route mouse idle. So it's going to only report the messages that begin with mouse idle, and it's going to report the rest of the message, the part of the message that comes after mouse idle. Secondly, I'm going to use zl.slice with the argument 2. And this is going to slice off the first two elements in this list and give me only those two elements. And there you go. Now I have the coordinates of my mouse as it is on the jit.world window. However, these are again not normalized, so I need to know the size of the window and I need to divide these coordinates by the size of my window. And I can do this by using the getAttr object. This is going to query object attributes, as in if I give it an argument, which is an attribute of another object, it can actually get that attribute, get the value associated with that attribute. So if I say getAttr size, which is an attribute of jit.world, and if I connect the second outlet of getAttr with the inlet of jit.world, it should report the size of the window each time I resize it. So now the only thing I have to do is to divide this list by that list. And to process lists in this way, you can use the vexpr or vexpr. This object is going to evaluate a math expression for a list. And we can go very much in depth with this object, but I'm just going to show you the syntax for doing this specific task. So $F1, as in the float number or numbers going into the first inlets, divided by $F2, the float number or numbers going into the second inlet. Now I'm using float numbers instead of integers because the result of this operation is going to be a float number. It's probably going to be 0.32 or 0.75, and it's not going to be an integer value. So I'm using float numbers as the basis for this mathematical expression. So if I put the mouse coordinate in the first inlet and the window size in the second inlet, and then I can of course change the window size to make sure something is sent to the second inlet, I should be receiving the normalized coordinates of my mouse no matter what the size of my window is. Alright, so my window can be any size, but I'm always going to get two values, the x and y coordinates of my mouse as it is on the JIT world window, and these are always going to be between 0 and 1, 0 meaning all the way to the left or all the way to the top, and 1 meaning all the way to the right or all the way to the bottom. Alright, so we have gotten the normalized mouse coordinates. Let's put some exclamation marks in here because this was, well, this was the easy part. I'm going to be honest with you. Now's the fun part. Now is generating that visual grid using this information only. And since we are using this information only, I'm going to send this information to my jit.gen, in which I'm going to create my algorithm for generating this color grid. So to send messages to jit.gen, I need to put a message at the beginning of this data, and that is going to be the name of the parameter I'm going to be sending to jit.gen. And this can be, again, any name, but I'm going to be using prepend mouse pos, short for, of course, mouse position. So the final message when I hover my mouse over the window is going to be mouse pos something something. The first thing being the x coordinate, the second thing being the y coordinates. And this is going to go into jit.gen. Okay, now I'm going to lock my patch. I'm going to double click on jit.gen and I'm going to look at my jit.gen patch. Of course, it's going to throw a bunch of errors, going to say invalid message mouse pos because I have not defined mouse pos as a parameter. Right? If I take this as my starting point, this in1 and out1, in1 being the empty matrix coming in and out1 being the result of this entire algorithm, first I'm going to define my parameter. Param mouse pos, and then the initial values 0, 0. These two zeros are necessary because they are telling mouse pos that the incoming parameter is a 2D vector, which is a very fancy way of saying it's going to be two values. It's going to be two values together with the name mouse pos. Okay, now I cannot really use in1 in this algorithm because the incoming matrix is empty. In1, no matter which cell is being processed in jit.gen, and jit.gen will process all the cells together, they're all going to just give me 0 because the matrix is empty. However, I can use norm, which is going to give me the normalized coordinates of the input matrix. So for each cell in the matrix, I'm going to get a different value, well, a different 2D vector that is going to reflect the coordinates of that specific cell in the matrix. Okay, so let me show you how this works as we try to figure out this algorithm. So let's get on our imaginary blackboard. Here we are. So imagine that I am a fantastic painter, and also imagine that this little approximation of a rectangle is, well, this is our matrix, right? This is the resulting image, and this rectangle is comprised of a lot of different cells and or pixels. Now, if I use norm, all of those pixels are going to have two values associated with it, and x coordinates that goes from 0 to 1, depending 0 being all the way to the left, right, 1 being all the way to the right, and it is going to have a second value which is going to be the y coordinate, and that is going to again be between 0 and 1, and it is going to be 0 if it's all the way to the top, and if it's going to be 1 if it's all the way to the bottom, and if it's anywhere in between, it's going to be anywhere in between. For example, this would be something like I don't know, 0.25 and 0. 0.25 on the x-axis, 0 on the y-axis. So all pixels are going to give us this information in our jit.gen patch. Now let's start thinking about this by thinking of the columns. So let's just do a single dimension before we just expand this into a grid. And let's imagine, for instance, that our mouse is at this position. And let's imagine that I have a perfect eye for these things so that this is 0.25. Now, the fact that the x mouse coordinate here is 0.25 tells us that the width of this grid element, or the width of this column, is also supposed to be 0.25. So I want to find a way where each pixel has a unique value that tells us in which column it's supposed to be, column number 0 or 1 or 2 or 3. Right? In this case, these would be column 0, and these pixels here would be column 1, and these pixels here would be column 2, and these pixels here would be column 3. Again, imagine that these are all proportional and I am a fantastic drawer, even though that is not the case. So how do we find this information out? How do we calculate this? Well, it's actually surprisingly easy. All we have to do is to divide the coordinate of the cell by the mouse position. In this case where we are working on a single dimension, we have to take the x-coordinate of each pixel, the normalized x-coordinate of each pixel, and we have to divide it by the x-coordinate of our normalized mouse position. So what does that give us? Let's see. I'm going to close this. I'm going to go back into my jit.gen, and I'm going to, well, first of all, target the x-coordinates of both of these guys. I'm going to do this by using the SwissX object. SwissX here, SwissX there, and then I'm going to divide the x-coordinate of the cell by the x-coordinate of the mouse, and let's just send it out for now. Let's just see what happens. Now, of course, nothing will happen now because I need to send a bang to this jitter matrix for it to, send its contents to jit.gen and for the visual output process to be triggered. But we can simply use the second outlet of jit.world, which is going to send a bang per frame, and we can connect it to jit.matrix. So if I have my mouse here, okay, so something is happening. You can see it is visually reactive. There are no colors, it's black and white because we are getting singular positions. And there are not really columns, but there is this very first block that is reactive to the X position of my cursor. So maybe it's easier to look at this in terms of numbers before we turn this into something meaningful for our visual output. Because what I'm imagining is, my guess is, my gut feeling is that from the beginning, the first block is going from 0 to 1, because let's say this is 0.25, and the pixels at that specific location also have the x-coordinate of 0.25, which, when divided by 0.25, is 1. And as we go on, it is increasing from 1 to 2 over the course of the next column, and then 2 to 3, 3 to 4, and 4 to 5, and so on and so on. But of course, since jit.gen or jitter visual output system is going to take 1 as the highest possible value for any color or brightness, anything after 1 is just white. But again, to view this visually, let's use jit.cellblock, which is going to show us the contents of a jitter matrix, not in terms of visuals, but in terms of values and numbers. Okay, so if my mouse is not in the window, well, it is just nan, as in not a number, or inf, short for infinite. But as I have my cursor on the window, look at what's happening. I'm getting these dynamic values. So if I have it here, for instance, what do we have? Well, it starts from 0, then it keeps going up and going up and going up, and it reaches the point of 1 around here, right? You can see this little scroll bar here. That is roughly the first column of our system, right? And as I've said, it continues from that point. It goes all the way up to 2. That would be the second column. And then 2 all the way up to 3. And that range of values would be the third column. And then all the way up to 3.83, because I imagine the size of the x-coordinate or size of each column is not perfect. That's okay. That's also how the P5JS sketch behaves. So first of all, how do we collapse these into integer values? Right now, this is 1, 1.1, 1.2, and so on and so on. But I just want the first column to be 0, the second column to be 1, all the pixels should be 1, and then the next column, all the pixels should be 2 and 3 and so on. So shortly said, shortly put, briefly explained, I just need to take out the fractional components of each float number. If it's 2.81, I don't care. 2.51, I don't care about the 0.51. I just want that 2. And going back into the jit.gen patch, there is an object that deals exactly with this problem, and that is called fract. Oh wait, not fract. Fract is going to return only the fractional component. So if I only wanted 2.51, if I wanted to receive 0.51 from 2.51, I would use fract, but I instead want to use floor. Floor is going to round a value down to the nearest integer value. So if I do this, as you can see, the visualization has changed a bit as well. Now I'm not getting those gray, graded tones. It's just black or white. It's almost like a step function if you are familiar and comfortable with shaders. In any case, if I go back to my jit.cell block, I do see that it's just 0, 0, 0, 0, and then just snaps to 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 3, and so on. So we have achieved what we wanted to achieve, but now we have to normalize these values, right? Right now these go from 0 to 3, but these should go from 0 to 1 so that our visual and algorithm can work with normalized coordinates. And this is surprisingly simple to do. All we have to do is multiply the result of this operation with the x component of our mouse coordinates. So we first divide the normalized cell coordinate, the x component of the normalized cell coordinate, with the x coordinate of the mouse, the normalized x coordinate of the mouse, and then we floor that value, and then we multiply the resulting value again with the normalized x component of the mouse. And would you look at that? Now, this is grayscale, but on terms of columns and on terms of the P5 sketch that we are trying to adapt into Max MSP, this is exactly working like we expect it to. This is exactly working as it should. Lovely. All right, so let's add some color to this system now. Right now, this value is just going throughout one, meaning all planes are receiving the same value, meaning that they are all, the same color. When merged together, they are going to be either gray or white. But now we are running into a problem because, well, this system, the P5JS, the system of the P5JS is working on the HSL or the HSB color system, that is hue, saturation, and brightness. So this value that we have just created or calculated should be the hue. But jitter and Max MSP is going to work with RGB value. So if we calculate this as an HSB or HSL value, we have to convert it into an RGB value before sending it out of jit.gen. And luckily there is an object that does exactly that, and it's called HSL2RGB. This object is going to expect a 3D vector, so three values together representing the hue, saturation, and lightness of a color, and it's going to turn that into red, green, and blue components. And that we can send out of our jit.gen patch. Okay, so let's define, by using the vec object, a 3D vector. Now again, 3 zeros. The first one is going to be the hue, that is what is being determined by this operation. The second one is going to be empty, that is going to be the saturation, and by default and always this should be 1. The third component, the third one, is going to later be the rows of our grids, but for now, as it's going to have a default value, I will make it 0.5. O would be 0 brightness or 0 lightness, meaning just black color, and 1 would be complete lightness or complete brightness, meaning just completely white. And 0.5 is just in the middle. So this being sent to HSL2RGB and that being sent to out1 should ideally work. Yes, look at this, beautiful. We have got this. We have received our HSL color wheel represented by dynamic columns in JIT world, in Max MSP jitter. And as you can see, it is mouse reactive, it is reactive and interactive in the same way as the P5JS sketch. And it can be very high resolution, or it can be just a few nice blocks. You can also slowly change the grid resolution, or the column resolution in this case, and see all these nice colors appear, and the overall color composition change. A very nice effect. But okay, how do we apply this to rows? How do we apply this to rows? Well, it's fairly simple. It's actually very, very elementary, because I'm just going to copy this entire thing. But instead of saying Swiss X, I'm going to say Swiss Y. That should be, in principle, that should be the only thing I need to add a second dimension on this generative grid. So now I'm getting the Y component of the cell coordinates, the normalized cell coordinates. I'm getting the Y component of the normalized mouse coordinates. Again, I'm dividing the cell coordinates by the mouse coordinates. I'm flooring that value, and then I'm multiplying the result once again by the mouse coordinates, this time the mouse Y coordinates. And this, instead of the hue, it is going to determine the brightness of the color, going from 0 to 1. Let's see how this looks. Okay, so this is not the P5GS sketch, right? But it is getting there. It is a grid, it is interactive, and the columns and rows are matching the color elements we want it to match to. However, this begins from the 0 point. This begins from 0 brightness, and 0 brightness is no color, right? So there is always going to be this section of our rows where it's completely black, and then it kind of starts fading into a color. If I kind of exit the window, it creates a very specific, creates a very specific set of columns. But that is a glitch, that is a bug you can use to your advantage. To fix this, however, we have to work with the range of values we are generating from the Y coordinates from our rows. Right now this is from 0 to 1, and a simple fix for this would be to simply scale this range of numbers that go from 0 to 1 to a range of 0.5 to 1. So let's take 0.5, kind of bright but not really bright, as our starting position, and let's go to complete white as hell brightness from that point. And if I do this, there we go. You can see this is pretty much exactly the same thing as the P5GS sketch. We have generated an interactive grid that takes a static jitter matrix as a starting point, and it only uses the mouse coordinates to calculate the width and length of each grid element and then colors them accordingly. Just to compare it once more, this was the P5GS sketch, this was our starting point, and here is our Max MSP patch. So here you have it. Now this is not so elementary stuff in terms of algorithms, but the end result is elementary. But as we go further with other P5GS sketches from this book and adapt it into Max MSP, you'll see that these grid techniques are going to be very useful for generating color palettes and interpolating color palettes. But just with this patch, you should be able to come up with your own variations, your own rules for generating color, and use these grids for goodness and aesthetics and art, and have a lot of fun doing it. Until the next video, thank you for watching.